This is for question number 3. Two bodies, M, which is on a table, slopes upwards an angle of 30 degrees, and M, which is connected to a light inextendable string, frictionless pulley. Coefficient of friction between the mass and the table is mu. So coefficient of friction is mu. Mass M is moving up the slope, so that's the direction. Clearly label the forces. Okay, so we will have one vertical force here, which will be the weight force, and that will be capital M times G. We will have a normal reactive force, which is perpendicular to the surface. We will have a frictional force, which is mu N, and we will have tension. Of the dangling, we will have tension, and we will have a small m g, being the 6 forces that exist in this particular case. Okay, so now we are told in part B, part 1, that big M is 4 and small m is 6, and that mu is this. Find the normal reactive force. Okay, so the normal reactive force. So I've redrawn my diagram. This is 4G because capital M is 4, and I'm wanting to find the normal reactive force on okay, so I'm going to break this into 2 forces. That's 30 degrees. This is 4G sine of 30, which is 2G, and this is 4G cos of 30, which is 4G root 3 on 2, which is 2 root 3G. So the normal reactive force is equal to 2 root 3G. And the question's asking then, hence find the tension in the string, hence find the resultant force of the system and the acceleration. Okay, so we don't have the acceleration. So what I'd like to do is I would say the resultant force in the direction of motion, which is up, will equal T minus any forces in the opposite direction, which will be 2G and root 3 on 3N, and root 3 on 3 times 2 root 3G should be, well, the 3's will cancel, that should leave 2G. And I have 4 times A equals T minus 2G minus, so that there is also equal to 2G, so minus 4G. So that's equation number 1. Looking at the dangling force, I'm going to have the resultant force in the direction of motion, which is down, will equal 6G minus T, and that 6A will equal 6G minus T. Therefore, T equals 6G minus 6A. T equals 4A plus 4G. I can make the two T's equal together and go 4A plus 4G equals 6G minus 6A, which gives me 10 A's equal 2G. A equals G on 5 as being my acceleration. T will equal 6G minus 6 times G on 5. T will equal, all on 5, 30G minus 6G. T equals 24G on 5. So I found the tension, I found the acceleration. What else was the question asking? Tension is 24G on 5 newtons, acceleration is G on 5 meters per second squared, and the resultant force of the system. Okay, so I've redrawn all my forces down here. The resultant force of the system I can see as a totality. I am moving in this direction. this mass is moving up the slope, this mass is moving down. So I can see the whole system. The resultant force in the whole system will be any forces in the direction of motion, 6G plus T, minus any forces in the opposite direction of motion, which is T minus 2G minus friction, which is 2G. And all of the masses is 6 plus 4 times the acceleration. Sorry, that's the resultant forces of the system. So I've got the T's cancel, 6G minus 2G minus 2G. The resultant forces of the system is 2G. So all the forces going in one direction minus all the forces going in the opposite. The resultant force of the whole system is 2G. And of course, I can find the acceleration of the whole system, which I know was G divided by 5. And I can find that out because I've got 6 plus 4 times acceleration is 2G, 10A equals 2G, A equals 2G on 10, A equals G on 5, same answer. So that the resultant forces of the whole system, think about all the motions and add all of those that are going in the direction of motion and minus all of those going in the opposite direction of motion. And of course, these two forces have no impact whatsoever because they're balanced, because the particle didn't leave the surface. Okay, so now I've redrawn all of the forces from the first part of the question when mass m was going up the surface. Now we're looking at the general case, angle of inclination, that's now theta not, okay, so I need to then change these to be cos theta and this to be sine theta. And we're looking at the point where it's in equilibrium but about to move down the slope. So since it's about to move down the slope, my friction will go up the slope because it's always going to be opposite to the direction of motion. So that's mu times n. So if air is about to move at the point of moving, then R equals 0. So anything in the direction must be equal to each other. So therefore, T plus mu n must equal mg sine of theta, because this is the only force that's going to move this thing down the surface, and these are the only two forces in the opposite direction. Since it's about to move, this particle back here isn't moving, therefore T equals small mg. So I've got small mg plus mu times n, and n is equal to capital Mg cos of theta, should equal capital Mg sine of theta. And what do I need to find? Find capital M. Okay. Mu capital Mg cos of theta will equal capital Mg sine of theta. Oh, I might move this over to there. So I've got a capital M here. I've got a capital M here. Therefore, small mg equals capital M g sine of theta minus mu g cos of theta. Therefore, capital M will equal mg on top of g sine of theta minus mu g cos of theta. And I can see a g that will cancel. Therefore, capital M equals small m over sine of theta minus g cos of theta. And that's going to be my expression for capital M in terms of theta, small m, and g.